So this is section 4.5 dealing with what's called the quantum mechanical model of the atom. As you're going to see very shortly, the quantum mechanical model of the atom is not something we can study in any detail here. Okay, we just can't. We're going to start off by looking at what's wrong with the Bohr model of the atom. I think we kind of already know what's wrong with it, considering there are over 100 elements, there are over 100 line spectra, and Bohr can explain some of them. That's a big problem. Then we're going to go over the key features of the quantum mechanical model. And as I said, it's not something we can delve into in any great detail. And then we're going to back up and consider the Bohr model of the atom again, or the Rutherford model of the atom again, and in a couple of different situations apply physics principles to solve problems. And those problems will involve speeds of electrons in atoms, and they will involve alpha scattering. So we're going to go way back a couple of days. To begin with, what's wrong with the Bohr model of the atom? It's limited to only one valence electron. And that's what all of these elements in group 1A, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, I think I got them all, but I might have missed one. They all have one valence electron. And because of that, for whatever reason, they all follow this rule. This is nothing you need to write down. It's nothing you need to know. But if you take out your formula sheet or your energy level diagram for hydrogen, and I'm going to ask you to look at the side that has negative 13.6 at the bottom. And I didn't get into this with you before because, quite frankly, we didn't have as much time as we have today. But for hydrogen, E1 is equal to negative 13.6 eV. So if I were to put 1 in for N here, I would have 1 over 1 squared times negative 13.6 eV. That's what I would get. Go ahead and put negative 13.6 eV in for E1 and use N equals 2. So you're going to take 1 divided by 2 squared times negative 13.6. And what you get, unless I'm mistaken, is about negative 3.4, which is E2 on your diagram. And if you take negative 13.6 and you multiply by 1 over 3 squared, I don't know how good my memory is here, I think you're going to get about negative 1.51, which is E3. And we've talked about this before. Armand, who is not here today, had asked, why in some energy levels is it not following that same pattern that we see on hydrogens, that the energy levels get closer and closer and closer together? That's because for all of the group 1A atoms, for hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, this is the formula that predicts the energy levels. And that was the formula that Bohr came up with. And there's a way to calculate what E1 is for hydrogen, and there's a way to calculate what E1 is for lithium and for sodium, and etc. So what I'm saying here is, when I say the Bohr model of the atom is limited to atoms with one valence electron, is not, everybody, that we still don't have photons emitted because electrons drop energy levels for the other atoms. All we're saying is Bohr can't calculate the formula used to predict the energy levels. The formula is totally different. As soon as you get to helium, things get out of control. That extra electron really makes things difficult. So that's what we mean. Bohr is able to come up with a formula for the energy states, the values of them for group 1A, but not others. One thing that definitely Bohr can't explain is the relative intensity of the spectral lines. So, for example, when we looked at the hydrogen line spectrum through a diffraction grating, you saw a red line, you saw what I'm going to call a greenish line, you saw a blue line, and you were not able to see the violet line. It was too dim. And what that means is whatever electron transition in hydrogen takes place to produce the violet line, which by the way is 3 to 2, it doesn't happen very often. It's dim because there aren't a lot of photons coming out of excited hydrogen gas with that wavelength, which means there aren't a lot of electrons in hydrogen making that transition. Whereas the red line, which happens to be from 6 to 2, is very bright. In fact, I think it's the one where you get the brightest intensity. The green might look brighter only because your eyes are more sensitive to green, but I believe the transition from 6 to 2, which produces the red, happens a lot more often than the other ones. I could be wrong. It doesn't matter. Some of these transitions happen more often than others, and Bohr just shrugs his shoulders and says, I don't know why that's the case. There is something called spectral splitting, sometimes referred to as Zeeman splitting. And under the right conditions, usually by exposing the gas to a magnetic field, when you look through the diffraction grating and you see, for example, that red line in hydrogen, if you expose the gas to a strong magnetic field, that line might split into 2 lines, or it might split into 3. And it could be, and this is not about hydrogen, but it's about other ones, that if this is where you're seeing that one line, when you expose it to a magnetic field, that line is still there, but you get another one here. And this one is dimmer. Or it could be that what happens is where that one line is, you end up with 2 lines. And the middle line is just not there anymore. Sometimes you'll end up with 3. There's a lot more going on inside of atoms that Bohr is unable to explain. And I would say to you that the first 2 are the most important things for you to know. You're certainly not expected to know this is called Zeeman splitting, but you never know when you might see something like that on an exam, particularly a diploma exam. So let me just start by saying the quantum mechanical model fixes everything. The quantum mechanical model of the atom, whatever it is, can explain all of the line spectra of any atom. It can explain the relative intensities of all of the lines, and it can explain why there is splitting of spectral lines under certain circumstances. I just want to give you a bit of a historical background here, because when you talk about the Dalton model, it's pretty clear it was John Dalton. Thomson, J.J. Thomson. Rutherford, Mr. Rutherford. Bohr, Niels Bohr. The quantum mechanical model of the atom was developed over a period of time by a number of people, but it's almost always associated with Erwin Schrödinger. And some of you might be familiar with this, Schrödinger's cat fame. The experiment with Schrödinger's cat, where the cat is neither dead nor alive. And we're not going to talk about that today unless you want to later on, okay? I've already had the discussion with many of you. So it's often called the Schrödinger, well, it is called the Schrödinger equation. So first of all, the quantum mechanical model of the atom has the following features. It is not a visual representation of the atom. We do our best to students, not just in high school but post-secondary, to try to say this is what it's like. But you know how the Dalton model is like a billiard ball? You can visualize that, right? The Thomson model is like plum pudding. Even though you may not have ever seen plum pudding firsthand or tasted it, you know what I'm talking about. The Rutherford model is like a planetary system. I think you kind of get the idea. As soon as we got to the Bohr model of the atom, you know what it's like? You know what the Bohr model of the atom is like? I'm not saying this is what an atom looks like. It's like a book in a bookcase that has a certain number of shelves. And if you want to put the book someplace stable, you can put it on this shelf or on that shelf or on the next shelf or on the bottom shelf. Or you can throw it away and not have it in the bookcase, which means it's an electron that's ionized. But we can still kind of visualize what it means. Quantum mechanical model is so far gone from anything physical in our mind that we just can't wrap our heads around it at this point. This is a scan of the title page of section 7.1 of a physics course I took. I took 2 courses that used the same textbook. This was in my 4th year of physics, and this is called the Schrodinger wave equation in spherical coordinates. So, I still remember my prof's name. If you were to ask Jerry Moss, what does a hydrogen atom look like? He would say, it looks like this. That's all he would say. He would say, I can't tell you what it looks like. I can tell you about the equation used to describe the behavior of electrons in the atom. And this is for hydrogen. This is for all atoms, actually. You put in the parameters for hydrogen and you get a bunch of equations coming out, which match Bohr's equations for hydrogen. But you put in a bunch of other parameters for helium and you get different equations coming out for helium. So I'm just showing that maybe as kind of shock value. You don't even understand what some of those symbols mean, right? And I'm not talking about letters. I'm talking about functions, like this thing. Well, if you've taken calculus, and there's at least one person in the room who has, you'll recognize that as a derivative. It's a derivative of some weird symbol, but it is a derivative. You will recognize, Sasha, this as a second derivative, but notice that the variables are different in here, right? This, I'm going to call that d, is d psi d theta. This is d2 psi d phi squared, which everybody else listening to Sasha and my private conversation have no idea what I'm talking about. But there's higher level math here. And to give you an idea of the complexity, I couldn't learn any of this until my 4th year of physics because I had to take 4 years of calculus to get there. Okay, so even the calculus that you learned wouldn't be sufficient for you to be able to work with this equation. So it's highly mathematical. This is the point. It's a highly mathematical, but it's not geometric. Geometry is a type of math, right? But geometry deals with shapes. It's not telling you what an atom looks like. It's not telling you the shape of an atom. I'll do my best to explain the shape in a bit. Here's the biggest thing, and the one thing for sure you need to know in case you're asked about something relating to the quantum model. The quantum mechanical model of the atom does not deal with where an electron is. It deals with the probability of finding an electron in a place. It's fuzzy. And the first time I kind of heard that description, I was a little bothered by it because I'm thinking this is supposed to be the best model, that it can't definitively tell me the answer to a question. It just says, it's kind of over here or it's kind of over there. When you're dealing with many atoms, probability is very useful. Okay? I may not be able to tell you which particular atom undergoes an electron transition, but I can tell you in a container of gas that the probability of an electron going from 6 to 2 is 48%. Whereas the probability of an electron in hydrogen going from 3 to 2 is only 4%. I made up those numbers, okay? But the point is, whatever those percents are for the probabilities, they match the brightness of those lines. All right, so I'm going to take an opportunity here to contrast what Bohr says hydrogen is like and what Schrodinger, or the quantum mechanical model, would say it's like. And this is a graph showing Bohr hydrogen in the n equals 1 state, which means the electron is in the ground state. And on the vertical axis, we have the probability of finding an electron at a particular distance from the nucleus. How many of you are used to thinking of probabilities as percentages? Okay, so the probability of tossing a coin and having it land heads is 50%. In math and physics, we like to use not percentages, although in math 30-2, I think you use percentages. We use decimals. So a probability of 1 is 100%. What is this graph saying that Bohr says about a hydrogen atom if it's in the n equals 1 state? He's saying the electron is at this distance, period. End of story. It's not a little bit closer. It's not a little bit further away. It's not over here. It's at this location. the first radius. And the curve that I draw here for the quantum model is certainly exaggerated. The probability of finding the electron in an n equals 1 state, it turns out, really is not 100% being at this distance, but it has the greatest probability of being at that distance. There are probabilities that the electron can be found further away from the nucleus or closer to the nucleus, even though it's in the n equals 1 state. And that seems weird. It does. It seems weird to me. In what energy level is this electron in? It's at negative 13.6, period. But the physical location can be different. The physical location can be closer or further away from the nucleus. If you remember anything, it's about the Bohr model being certain and the quantum mechanical model being probabilistic, uncertain. So what does this look like? Well, and this is one of the more difficult things I have to try to teach, because I suppose I could just tell you the quantum model deals with probability, the Bohr deals with certainty, and end it there. But I think then that would just leave you hanging intellectually. So if I compare now what we physically see, if you could look at an atom, and keep in mind I'm drawing both of these in two-dimensional space, they would actually be spheres. Of a hydrogen atom in the n equals 1 state, the electron is in a perfectly circular orbit, never wavering, never varying from that distance. So if I look at the electron, I'm always going to find it here. One of the things that's hard to wrap our heads around is the quantum model of the atom never ever talks about the motion of the electron. It's not in an orbit. The quantum mechanical model says the electron is here on the right, then it's there. And then you look a short time later, or a year later, I don't care, and you discover the electron is in a different location. And you keep taking glances, and at different points in time, you see the electron in different positions. But the highest density on that diagram matches the Bohr model of the atom. Okay? And you need to understand, particularly for what we're going to do in a minute, that this doesn't invalidate the Bohr model of the atom. The Bohr model of the atom still works, is still valuable. What this quantum model is something that turns into Bohr's model for hydrogen and turns into Bohr's model for lithium and sodium and etc. And that really is it. That's the quantum model of the atom. It's able to, though, accurately predict the spectra of any atom and can also explain spectral splitting. It turns out that rather than just having one quantum number, the energy level number, there are other quantum numbers. There's something called angular momentum and spin and all these other things. I don't even want to talk about that. I should take that out of my notes. The bottom line is that formula I showed you can create a special formula for each of these atoms. But it is complicated. Like one of the courses I took, not the whole course, but a big chunk of the course was studying the electron behavior of hydrogen. This is a university course. You would need a full course to learn about the electron behavior in, I never even knew this thing existed, terbium. It would just be some whole course. I don't think there's a single person on the earth right now that has studied each of these in depth. And probably they would be studied using computers now rather than doing the math on paper. And by the way, out of that proposal of the standing wave comes this idea as well. So we're looking here on page now 23, thank you, of your unit handout. And we're going to be going back and just doing some physics that you might encounter on exams. It turns out that the radius of the electron's orbit in hydrogen according to Bohr, and I don't mean to say according to Bohr like he's wrong. He's right. He was able to predict this. Can be found by taking n squared times the first radius, which is this number here. So if I ever want to know the radius of an electron in hydrogen when it's in the third energy level, I take this number and I multiply by 3 squared. And the question is, how fast is an electron moving in the third energy level of hydrogen? The first thing to note is you can't use an energy level diagram to answer this, because those numbers on energy level diagrams are arbitrary. It depends on where you put 0. What we're going to do is answer the question this way. What would you do if I gave you the radius of a satellite around Earth and said, how fast is the satellite moving? Well, you would say that the net force is a gravitational force, which means ma is g mm over r squared. You remember doing this in Physics 20? And the acceleration is centripetal. So that means it's mv squared over r equals this. I'm not going to do this problem. The mass that cancels is the satellite mass. You could do it. You could find the speed. If in this course, in Unit 2, I said, and I gave you the right information, how fast is an electron moving in a magnetic field, then you would have done this. Right? And you'd cross multiply and you'd find the speed by knowing the radius and all that other stuff. But an electron in an atom is in a circular orbit. There's a net force towards the center caused by electricity, not magnetism and not gravity. So to solve this problem, this is a hydrogen atom, by the way, in its simplest form, proton and electron. You would say that this net force is equal to the electric force. And they are equal. It's not two forces with the same magnitude. They are the same force. I just don't see any need to put vector symbols on there. I don't know what the point would be. So this is Ma. And Christian, I'm really glad you asked what you asked. It's going to fit nicely with one of the questions we're going to answer here. This becomes kqq over r squared, where q1 is the charge of an electron and q2 is the charge of a proton. And of course, this is a centripetal acceleration. And I'm not going to write a subscript, but that mass is the mass of the electron because it's the thing accelerating. So we're going to change the centripetal acceleration to v squared over r. And let's forget about the math for a second. Let's look at the formula that has physics in it. You're trying to find that speed. So going left to right, do you know the mass of the electron? Yes. Do you know Coulomb's constant? Yeah. Do you know the charge of an electron and the charge of a proton? Yes. Are we told the radius of orbit? Well, no, not directly, but you are told that Rn is n squared r1, and you're told what r1 is. You wouldn't have to memorize that or the formula. You would be given this information in the context box. So r3 is equal to 3 squared times r1. It's been a while since I've done this, but can you confirm that I wrote that number down correctly? Okay. So we're going to calculate r3 so we can put it in here to find v. I'm going to go ahead and rearrange this for v right now. V squared will be equal to k q over m r. One of those r's cancels. So then we would take the square root of that. All right, so let's calculate 9 times 5.29 multiplied by 10 to the negative 11. This is R, 4.761 times 10 to the negative 10 meters. So K, 8.99 multiplied by 10 to the 9 times the charge of an electron times the charge of a proton. So I've just, rather than me going times the same thing, I'm just squaring it because Q and Q are equal. I need to divide by the mass of the electron, and I need to divide by the radius, and then I need to take the square root. And we've all come a long way. You understand that we don't need to write down every number that we're using. So what do I get? .28 times 10 to the 5 meters per second is the speed. So the physics you apply to analyze satellite motion, which is circular motion due to gravity, and the physics you apply to analyze charged particles in a magnetic field, which is circular motion caused by magnetism, is the same as the physics you apply here. It's just that it's circular motion applied by electrical forces. Does anybody have any questions with that first example? All right, now, what is the de Broglie wavelength of an electron in the n equals 3 orbit? Can you just confirm that yours says n equals 3 as well? Okay. So from the previous unit, Compton learned that the momentum of a photon is Planck's constant over the wavelength. De Broglie comes along and says, you know what, I'm going to turn that over on its head, and I'm going to say that the wavelength of an electron or any other particle with mass is h over momentum, but momentum of a particle with mass is mv. Hopefully, this being the very last topic of the previous unit is not too far in your memory, in your past. So what would the de Broglie wavelength be? Well, I need to take Planck's constant divided by the product of the mass and this speed. Only standard units here. And by the way, I had a conversation with somebody today in Sabre Support about different units, and last week as well. You know, if you're ever unsure when you were allowed or not allowed to use electron volts, then don't use electron volts. Because joules will always work, but electron volts don't always work. So I need to divide by the mass of the electron, and I need to divide by the speed. So this is the de Broglie wavelength. Might as well call it 1.0 times 10 to the negative 10 meters. That does not mean the electron is an X-ray photon. Okay, that's not what it means. I just misspoke, by the way. I said we might as well call that 1 times 10 to the negative 10. That would actually be 10 times 10 to the negative 10, or 1 times 10 to the negative 9. If that bothers you, I don't care. I don't want to get trapped in a conversation about rounding and math. Okay. Does anybody have any questions with the calculations for 2? Okay. Christian asked the question, how did Bohr get his hands on this information? And I said, well, it has to do with this underlying assumption that the de Broglie wavelength of the electron is a length that will fit the number of times in the orbit that the energy level is. And what that means is in n equals 3, the circumference is equal to 3 de Broglie wavelengths. I'm not going to try to draw 3 wavelengths around in a circle. It gets hard on my brain. Well, we know the radius, don't we? And circumference is 2 times pi times the radius. And I'm pointing out to you that we could find the answer to question 2 without ever finding the answer to question 1. 2 times pi times the radius. I'm going to have to go up a bit to find it. Was this the radius? I guess I can look. Yes, it was. This is the radius. So 2 times pi times the radius is the circumference. But 3 de Broglie wavelengths have to fit in this circumference, so if I divide it by 3, I get the answer. And now I'm not getting the exact same answer because one of these involves Planck's constant to calculate. His hypothesis does. You understand that these are arrived at using different... Actually, the de Broglie wavelength has Planck's constant in it. This is arrived at in a different way. You understand that there are different constants, so you're not going to get the same thing. You could have found the de Broglie wavelength that way. So any questions with 1 or 2? Okay. So at lunch, some people were mesmerized by this. This is an animation showing alpha particles, which don't look like those dots, approaching a gold nucleus, which doesn't look like that yellow dot. And we were seeing if we could find, if we waited long enough, that we could get an alpha particle to bounce straight back. And there was one that was pretty close, wasn't there? We're not going to stand here and wait for it, okay? But I need you to understand that as any alpha particle gets closer to the nucleus, it's going to slow down and then it will be deflected. The closer it approaches to the nucleus, the more it slows down as it passes, and then it will speed up again after. And what's happening here, everybody, that was a good one, I should have grabbed that one, is the alpha particle is moving quite slow here because it's close to the nucleus, and that means there's a lot of electrical potential energy pushing it away. I know energy isn't a force, but think of it as pushing. And then it changes direction, and right now, instead of being slowed down by the positive nucleus, remember an alpha particle is positive, now the force is in the same direction as the motion, so it starts speeding up again. And the question I had asked is, if you had an alpha particle, and we're not going to find one, I mean I could stand here all day, if you had an alpha particle that happened to be I have to grab my screen capture tool. If you had an alpha particle which happened to be on a dead, straight-on collision course with the nucleus, it's going to hit straight on. The fact of the matter is, because it's repelled, it will never actually touch the nucleus. Because if it did, the distance between the charges would be 0 and the force would be infinite. So what happens is this, it comes in, it slows down and stops, but because it's hitting it's dead on, it's going to change direction and go right back from where it started. Does that make sense? On the other hand, an alpha particle here is going to be deflected. An alpha particle a little off center will be deflected back maybe. An alpha particle here will be deflected a little bit. You get my drift? Okay. So if the alpha particle comes to a stop here, then it has no kinetic energy. Right? But the alpha particle was moving when it was back here. So it had kinetic energy. Where did the kinetic energy go? Who can tell me where the kinetic energy went? And I'll give you a hint. The kinetic energy's gone, and then it comes back. Anna? Electric potential energy. I mean, if I could take this alpha particle and hold it here, just put my hand on the left side of it and hold it, I would feel it being pushed back towards my hand. That's because there's an electric force. So now let's take a look at the next question. So there's a background to the series of questions we're going to now do. And it's that this is the formula for electrical potential energy between two charges at a certain distance. This is new to you. This is not on your formula sheet, and it's not Coulomb's law. This is energy, and it's not over r squared. It's just over r. Don't worry about why. Okay? It's a fact. Here's the first question. During an alpha scattering experiment, alpha particles are observed to be scattered at 180 degrees. What does that mean? It means they come straight back. And what it means is this. As the alpha particle is way out here, moving to the right, it is moving quite fast. And it's far enough away from the nucleus that there's no electrical potential energy. As it gets closer, there's going to be a force pushing it backwards, slowing it down. This is tricky because not only will there be a force slowing it down, but as it gets closer, the amount of force slowing it down gets greater. The force acting on the alpha particle when the alpha particle is here is less than the force acting on the alpha particle when it's there. So there's an electric force, and the electric force gets larger and larger and larger. But that means the acceleration gets larger and larger and larger. There's an awful lot going on here. But the big picture in terms of the energy, everybody, is that it has all kinetic energy here, and then because it deflects back 180 degrees, it has no kinetic energy here. And if energy is conserved, this potential energy at the closest point and this kinetic energy at the beginning are equal. Are you with me in principle on that? It's like saying the kinetic energy of a pendulum bob at the bottom is equal to the potential energy of the pendulum bob at the top. And then it's going to go back to kinetic, except with a pendulum, then it's going to swing back and forth. This, the alpha particle is going to slow down to a stop and then turn around, never to return. Well, for all intents and purposes. So what is the question? What is that distance of closest approach? Well, if the kinetic energy it has far away is equal to the potential energy it has at the closest point, then we can write 1/2 mv squared equals k q q over r. It's that simple. You're asked to find r. So r is going to be 2 times k times q over m times r. Over m. This is r. And sometimes you just have to go, I'm going to follow the physics. I've got to rearrange that, make sure it's, that's right. So the r moves up here, and I also need over the v squared. Does that look like I have all of the pieces covered now? Yeah.
Is it KQQ or just KQ?
It's KQQ. Do you not have KQQ on your handout?
I don't think so. I'll look later. Oh, I'm looking at a different one. It's good.
Are they both there?
I was looking at my formula sheet, but it was different.
Gotcha. Okay. So what you were looking at is electric field strength. So we have Coulomb's law, which has this suspicious nature to it, this appearance. We have electric field strength, which has this appearance. But electric field strength, there's 1 Q and 2 R's. And we have this, which is not on your formula sheet. Okay. So how's my rearrangement here? Okay. So we need to put in the numbers. Now, here's the problem, though. I know what K is, and I know what Q of the alpha particle is, but this is the gold nucleus. The second charge is the gold nucleus. Now, why does a gold nucleus have positive charge? Because it has protons. And we're going to study this in depth later on, starting actually tomorrow. But gold is atomic number 79. And 79 tells you the number of protons in the nucleus. So that charge on the gold nucleus is 79 elementary charges. Now, there is no need for me to calculate that. I don't need to take 79 times the elementary charge. Here's what I'm going to do. I'm going to take my calculator. I'm going to take 2 multiplied by Coulomb's constant, multiplied by the charge of an alpha particle, which I know is 3.2 times 10 to the negative 19, multiplied by the charge on a gold nucleus, which is 79 times the elementary charge. Divided by the mass of the alpha particle, .65 times 10 to the negative 27, and divided by that speed squared. Double check everything. There's a lot of numbers floating around here. So I am getting 1.6 times 10 to the negative 14 meters. There would be absolutely nothing wrong, everybody, with you calculating this, the kinetic energy, and then simply setting it equal to this and saying the radius is KQQ over that energy. There's nothing wrong with that. All right, question 2. Same scenario. What's the acceleration, the maximum acceleration that is experienced? Well, acceleration is F net equals ma. That's not what acceleration is, but you get my drift. We're going to have to use that formula. So where in this diagram, where will the acceleration be the greatest? That's a tricky question. Where will the instantaneous acceleration of the alpha particle be the greatest possible value? Exactly right. Closest to the nucleus, where the electric force is the biggest. And that net force here is the electric force between the two particles, between the nucleus and the alpha particle. But this is a force now. This is about force. The first question we did was solved using energy. So now that we know what R is, the distance of closest approach, we can calculate the electric force and set it equal to ma. If you look at this formula, if r is small, the force is big. Well, what we're doing is we're taking that distance of closest approach, the smallest r possible, to calculate this biggest force so we can divide by the mass. So what does this work out to? Well, we have to take k times the charge of an alpha particle times the charge of the gold nucleus. Here we go again. 79 elementary charges divided by the distance squared. This is a force. So k times q over r squared, and I missed the 1 there on my charge. So when I hit equals, this will be the electric force at that point, and it is a staggering 139 newtons of force. Think about that for a second. That is the force required to lift a 14 kilogram mass off the ground, which is about 35 pounds. That is the force required to lift a 35-pound mass off the ground, and it is being applied to an alpha particle. So this is the net force. So if we want to determine the acceleration of the alpha particle at that point, we divide that by the mass of the alpha particle. And you get a stupefyingly large acceleration. It doesn't even make sense. 2.1 times 10 to the 28 meters per second squared. It's only happening for an instant, but that's the acceleration. So we're going to do one more question. Can I borrow your handout for a second? Because the next set of examples are a challenge problem, and I can talk about them with you if you're interested. So during an alpha scattering experiment, we're going to do this one. Alpha particles are incident on a gold foil. They're deflected backwards. So if they are deflected backwards, then we are allowed to use this. Because if they're deflected backwards, that means they hit the nucleus, quote, hit the nucleus dead on, which means they have to stop and lose all their kinetic energy. What is the maximum speed? So I just said we are allowed to use this. That's 1/2 mv squared equals kqq over r. This is the maximum speed because that's where it's all kinetic energy. So we need to know the mass of the alpha particle. Do we know that? Yep. We need to know the charge of an alpha particle, the charge of the gold nucleus, Coulomb's constant. What are we missing? What is throwing up a roadblock here? Well, we don't know r, but r is the distance of closest approach. And you were told the maximum acceleration, which means you can calculate the maximum force, which occurs at the closest approach. So not only can we use this we can use F net equals Fe, and this is Ma equals KQQ over R squared. You know, maybe 10 years ago on a diploma exam, there was a question like this. I'd never seen the question before. It never even occurred to me to do this question. But I think that year when they first put it on the diploma exam, it was something like 10% of the province got it right. And that's the reason why we're doing them here, in case you see it. Okay? We need to find R, so we can put R here. For those of you in Math 30, this is a composition of two functions. We're using one function to find R, and then we're using that R in the second function to find V. So you need to take Ma, set that equal to KQQ over R squared to find R, then take that R and find the potential energy of the alpha particle to set it equal to the kinetic energy of the alpha particle. There is nothing simple about this question, especially given that this thing here is a new formula, right? So how do I find the net force? I take the mass times the acceleration, and I hope you understand I'm finding the maximum net force because I'm taking the maximum acceleration. And then when I find R with the maximum force, I'm finding the minimum R. That will allow me to find the potential energy at that point. So 6.65 multiplied by 10 to the negative 27 multiplied by the acceleration. Okay, not 139 newtons this time, but that's okay, it doesn't matter. So the mass times the acceleration gives me that. This number on my calculator right now, everybody, is equal to KQQ over R squared. Which means I need to take KQQ and divide by this number to get R squared, and then I can take the square root. .99 times 10 to the 9 times the charge of an alpha particle times the charge of a gold nucleus KQQ divided by that force. This is giving me R squared. So the distance of closest approach is that. And we did all that so we could determine R, so we could now calculate the potential energy at that point and set it equal to the kinetic energy at that point. So the potential energy is Coulomb's constant times the charge of the alpha particle times the charge of a gold nucleus divided by R. Just R because we're finding energy. What is this that I've just found? It's the mechanical energy of the alpha particle in the system. It's how much potential energy it has at the closest approach, and it's how much kinetic it has outside, way, way far away. So if that's the kinetic energy, I can multiply by 2 and divide by the mass. Whoops. Divide by the mass and take the square root. This is the answer to the question. And that, boy, as far as the two physics principle problems go, that one is near the top in terms of difficulty and complexity and amount of calculations and thought.